Okay, shall we start?
I think so.
Yeah. So, welcome to the second part of the SoGood workshop at ECMLPKDD 2020. I'm very pleased to present you Pedro Saleiro. Pedro Saleiro did his PhD in Porto. After he went to a postdoc at the University of Chicago, working with Raid Ghani, where he was involved in several projects with governmental and non-governmental organizations in projects for social good. He developed a software for defining the best metrics for this type of social good projects. And now he is back to Portugal and is working at a Portuguese company, FitZai, that is a well-known company working with streaming data and fraud detection, where he leads the group on faith, fairness, accountability, transparency, and ethics research group. So this is everything related with the topics of this workshop. So you are very interested in hearing you. Thank you for coming here, Pedro, and the micro is with you. Thank you.
Thank you so much, João, for the introduction, and thank you so much to the organizers for inviting me. It's really a pleasure to kind of talk about this work with this community more focused on Europe. And I'm going to talk about dealing with bias and fairness in data science for social good projects. As João mentioned, during my postdoc, I worked with Raid Ghani, and I was also mentor at the Data Science for Social Good Summer Fellowship at the University of Chicago in 2018. And I was really involved in all the projects of the Data Science for Social Good Foundation that is led by Raid. And most of this work is really inspired and is driven by Raid and his amazing work in these areas. So most of the projects of the Data Science for Social Good Foundation and the SSG Fellowship have many different organizations around the world, not just in the US. And usually these partner organizations usually have data, and they need some help on best serving the people that are addressed by their services. And we can talk about criminal justice organizations. We even had the projects with prosecutors and attorney general offices. We can talk about mental health facilities in the criminal justice system, healthcare, education, workforce development, many different policy areas. And these governmental and non-governmental organizations are really trying to help people, and they have data. And usually when they came to us, their primary goal was really efficiency. So they have this data, they have limited resources, so limited capacity for interventions to help people. And they really wanted to really maximize the resource allocation. So they really their primary goal was really to reach as many people that really need help as possible. What we observed over time when developing these projects is that often there was this tension between efficiency and fairness and equity, because machine learning models tend to be greedy, and what happened in practice is that we end up building systems for data science for social good that tend to help people that were easy to help. So not the really people that are hard to help, in which we had less data, often from minorities. And this faced us a problem in which we kind of needed to come to kind of a back to basics approach on really from scratch defining with these organizations what do we really want to achieve with these projects, and we don't really want to leave anyone behind, and we don't want to exacerbate any inequalities that are already there in the society. I also want to talk, and a little bit of an advertisement on, this year it's a very special and particular year in time, and the Data Science for Social Good Fellowship really moved online into this marketplace for data science for social good, which is called Solve for Good. And it's a marketplace where organizations can post projects and people can offer as volunteers. And it ranges from data scientists to project managers to people helping scope. So to the audience of this workshop, I probably believe that this is of your interest, and please check it out, and if you can subscribe and join the Solve for Good marketplace online. Today I'm going to focus on bias and fairness, but it's always important to keep in mind, and I believe you all are all aware of, and it's not the only thread of issues around data and AI, thread of ethical issues, as João mentioned, accountability, transparency, even privacy and data ownership. They're all different problems in AI, but today is really about bias and equity and fairness. And in this data science for social good projects is really about, if we don't want to take the risk of developing machine learning and AI systems that just optimize utility, or if the utility is just based on accuracy, on predictive accuracy or efficiency in the end, we might end up with interventions in systems that don't really reflect our values, because they tend to be optimized for efficiency that tackles just specific groups on population. Usually it tends to be with demographic distributions, with majority groups. So it's really important to make sure that really from the beginning we try to encode our values and our fairness values in these systems. And I think the main message, if there is one takeaway message that I want you to get from this keynote, is that it's not enough to make sure that we develop machine learning models that are fair. It's the full system end-to-end that needs to reach fair and equitable outcomes. And there are these two parts here in red, which is help make decisions and outcomes. Why? Because often in data science for social good projects, there is a human in the loop. It can be a social worker, it can be a doctor, it can be a judge, that receives the prediction from the machine learning model and as the final word. So it's the final decision maker. And before, these sort of decisions were solely based on this human expert, but now with data science, we are kind of complementing this human expert with the machine learning model predictions. But why should we just focus on the outcomes and not on the middle steps? Because this human might override the decisions of the model. We can have a perfectly fair machine learning model, but at the end, if the human has some sort of unconscious systematic bias, or doesn't trust the model in specific cases, we might end up with a system that provides outcomes that are not equitable. So it's really about the whole system, not just the model. And this is really the overarching kind of message that I want to pass. And there are many different steps involved in the systems. We have machine learning model, we have the actions, we even might have tailored and specific interventions for specific groups of people. And then we have the outcomes, and bias can be introduced in any source of this pipeline. And also one thing that is really important is you know, a small little disclaimer. My background is computer science. I consider myself part of machine learning community. I tend to try to formulate the problems as optimization problems, but sometimes it's unrealistic to aim for 100% fairness. And it's really important to understand what is the status quo, what is the real world baselines that are out there. And if we are already able to improve the current baselines, there is already an improvement in the status quo regarding fairness. And, you know, we have all these stages. So we have the world, we have data that is just an artifact that reflects a process that happens in the world. We have our AI and ML pipeline. We might have a human in the loop. We have the actions for these interventions. So imagine a case of project that I worked on in which we were trying to provide mental health outreach to people that were often cycling the jail system, so recidivists. And we might think of different types of interventions for different types of people. So one intervention could be phone calls, but what about homeless people that don't have phones? We can think about, in-person visits, but we have a limited capacity and limited budget and resources to have these kind of in-person visits. Are we going to repeatedly contact people or not? So all these different interventions might produce different outcomes. So bias can be introduced even in the type of intervention we tailor to specific people. And starting with data sources. We might have sample bias, might have measurement bias, we can have label bias. So really the choice of data source might impact the overall fairness of the systems. We have census data that can be linked somehow. We have data from different government agencies. I work in projects in which we have data from the criminal justice systems, from the courthouses, from the police, from public health organizations. And each of these data sources results from a process that usually there is a human inserting data when they are interacting with the citizens, and different sources of information might have different biases. And even you can think about, for instance, some in US, some data from police has different quality if it comes from police stations with less budget and less money to have fully automated and really quality data compared to other areas, richer areas in which data is very clean and very high quality. And all of these can introduce some sort of bias. Even the question of, we might be building our models in specific subgroups of our population or samples that don't reflect the target population in which we are going to deploy our systems. As I said, data quality might not be uniform across groups because some groups interact with public services in public services that are underfunded and the quality of the data is not so good. We might have minority groups and we need to come up with some sort of a strategy to deal with this really imbalanced data. The label bias is kind of one of the most striking problems we have, because all of these traditional supervised learning approaches rely on labels, and we assume that labels are trustworthy. But when we work with real world public policy data, that is not often the case, and they might be a result of a bias process. For instance, over-policing African-American communities will reduce in more arrests. And if we use arrest data as label to predict future criminality, we are introducing some sort of bias in our systems. One there is very striking. Often people assume that the only source of bias is data. If we have a perfect data set, then it's impossible to add any kind of bias. I know that um, you know, there are some sorts of different sources and different assumptions that different algorithms assume, but is very common in the wider audience, the public media, and even there was, I'm not going to talk too much about it, but it was a very recent discussion and polemic around some Jan LeCun statements about the only source of bias is data. And, you know, from real world experience, that's not really the case, what is in practice, because every single decision we make in our machine learning pipeline might introduce some sort of bias. For instance, record linkage. Record linkage is a huge source of bias because, as I mentioned before, we might have data from different sources, and we have to link this data. In US, often there is no national ID card. We have social security numbers, we have first name, last name, and we need to link this data. And we introduce two bias in two dimensions. We are, for some people, that should be just one record in our data set, we are multiplying these people and counting them multiple times. So we are affecting the group sizes and the prevalence across these groups. And also in terms of feature distributions, because often we use counts and aggregate features, and because we are now deduplicating people in multiple records, we are changing the distributions of features, and we are introducing some sort of bias on that regard as well. The target metrics we choose to optimize for. We usually select models based on our target metrics. So if we use different metrics, we'll choose different models, and different models might have different biases and different distributional fairness. Even one of probably if I point one huge gap in the machine learning literature regarding fairness is about thresholding. In data science for social good projects, we don't use 0.5 as threshold. We have limited resources. We have a tailored specific point of operation in our ROC curve in which we deploy our models. So the model might be fair if you use 0.5 as a threshold for binary classification, but in real world, how the model is deployed is in a very specific region of our ROC space. So just selecting that value for the global threshold, you can think about global total number of predicted positives. We can talk about specific tolerance of FPR rates. So imagine we select the model that maximizes recall at 1% false positive rate, for instance. Just changing from 1% FPR to 5% FPR to 10% FPR will have a huge impact in distributional metrics of fairness. And this is somehow a source of bias in the system as well. How we deploy, how we communicate. There are many different sources of bias in the machine learning pipeline, and it's not just the data. And then, as I already mentioned, the action intervention bias. Different people might react different for different interventions. There might be some heterogeneity across different groups. And there is also this human in the loop that might override the decisions. And at the end, what the system reflects is the systematic bias of the human, even if the model is fair. So this is really an ongoing process. As we deploy our machine learning models and they are live and they are in production and we retrain them, we need to continuously monitor bias and fairness and make sure that the system is producing the outcomes we aim for. And as we have concept drifts that affects predictive accuracy, that also affects the fairness that we get. So it's really a challenge. It requires lots of effort and really continuous monitoring. So we kind of believe that first thing to do in a project in data science for social good is with the stakeholders, we define what are the fairness goals, what are the equity goals that we have for the project. We need to measure and detect bias when we are building our machine learning models, compare with current baselines, understand the bias of current baselines or human expert decision makers. we should try to understand the root causes, and this is very hard, and there is not much research work on really understanding why we get these fairness results. Is really lacking in the research community, and I challenge you to try to tackle this issue of really understanding why do we get these disparities. It's because of all the things I mentioned. Is the data in the first place? Is because of the data science pipeline we use? Is because we have label bias, some sort of selection bias we have? What is the root cause for the biases that we might find when we measure? For sure we want to improve it. There is vast literature on bias reduction methods. We aim to mitigate the impact. That might also include provide some sort of training to the human in the loop, because once again, it's the whole system that matters. And as I said in the beginning, it's a continuous loop. We need to continuously monitor and evaluate bias and fairness all the time, not just when we deploy models. So how do we measure bias and fairness? There are so many different metrics out there in literature. Also, there is one thing that is somehow cumbersome, is that there is also no standardization in the nomenclature of the metrics. So you really need to be an expert in the field to really understand that different papers consider different names for metrics, but at the end, they actually account for same things as other paper that named it differently. I think this is for sure also a byproduct of the field being somehow incipient and very new in the machine learning community. Although the problem is very old, but this recent vague for the last 2, 3, 4 years is very scattered yet in terms of naming of metrics. But yeah, we have many different metrics. Some might make sense in specific applications than others. For instance, you know, there is lots of people mention statistical demographic parity or disparate treatment. It depends on the flavor you want to call it. That are metrics that don't really depend on the labels. In some sort of applications, it might make sense to consider these distributional metrics. But at the end of the day, if we are providing some sort of intervention, we really care about the outcomes. And with these metrics, we are agnostic to the outcomes because we don't really know if it was a false positive or false negative. We just care about distributing the predicted positives. So in real world data science for social good projects, statistical demographic parity really depends on the specific needs of specific projects, but usually we go for metrics that rely on the confusion matrix because it's really about helping people and it's about not hurting people. So we care about the outcomes. So this is a typical table you get from Wikipedia, from receiver operation characteristic table. And, you know, most of us kind of are really familiar with all these metrics. And for each one of these metrics, these metrics can become a bias metric if we compare these values across different subgroups. So instead of calculating false positive rate for all our sample in a test set, we might separate and break down the false positive rates among male versus the false positive rate of female, of white people versus non-white people. And as soon as we use these metrics for subgroups, we are starting to understand the bias in the systems. And I didn't make this claim in the beginning about what is bias because I assume that this is a machine learning conference. We're not talking here about statistical bias. We are talking about disparate predictions across different groups in this context. And you are for sure very familiar that this is somehow the oversimplification, and the terminology that we use is about, you know, disparities, bias, fairness. They tend to be used interchangeably. And there are also some well-known trade-offs. This one is actually, you know, people usually tend to say these types of demonstrations are demonstrations by Wikipedia, in the sense that Basically, we just need to go to the definition of these metrics, and we come up with this result quite straightforward, in a quite straightforward way. So basically what this says is that basically we are putting false positive rate as a metric that depends on prevalence, false discovery rate. So false discovery rate, also usually known as error rate, it's 1 minus precision, and false negative rate, and 1 minus false negative rate is true positive rate or recall. So by putting false positive rate as a dependent variable on these other metrics, when we compare these between two groups, so imagine that we have a ratio here of this false positive rate for a group A, and we divide this same expression for a group B. If the prevalence of group A is different from the prevalence of group B, it's not possible to have similar ratios of false positive rate, which means parity, and at the same time as false positive rate and true positive rate. We cannot achieve at the same time this is the so-called and usually referred in the community equalized odds. It's not possible to achieve equal false positive rates and equal true positive rates across groups if the prevalence is different across groups. But, you know, this is often used as an excuse. So, oh, that means there is some sort of incompatibility across metrics. So that means we cannot really be fair because we cannot achieve fairness in all the metrics at the same time. And this is really kind of, I must say, a lame excuse. Because not all bias and fairness metrics make sense in all applications. And the ProPublica article about Compass is really an example of that. ProPublica article is not about biases in criminal justice system. It's about how different stakeholders perceive what is fairness. And different people define fairness in different ways. And there is no actual consensus. So if you are aware of the story, so ProPublica audited this Compass, which is a algorithmic risk assessment tool used in US to determine bail and the bail amount for people that are incarcerated. And what they found is that the false positive rate for African Americans was 2 times the false positive rate for Caucasians. And they say that in the article, and the company that developed the algorithm replied back saying that we are aware of that. Our fairness goal is precision calibration, or simplifying, equalize false discovery rate across groups, or equalize precision across groups. And we get that. And actually, when I audited the data set, you see that FDR is equal across groups. False positive rate is twice for African Americans. But the real question is, who decided that calibration, precision calibration, false discovery rate parity should be the fairness goal in this system? And the conclusion is that this was a somehow arbitrary decision from the North Point company. And this is really what it is at stakes in terms of our society, because we don't have frameworks, we don't have legislation in practice. People are not really aware, are somehow fairness blind. Some people might come up with their own definitions, and often these are arbitrary decisions. And because of that, we at the Center for Data Science and Public Policy, myself, Raid Ghani, and Kit Rodolfo, we kind of start to kind of try to help our stakeholders, our policymakers in these partner organizations to kind of help them decide what metric makes sense when and for each application. And we came up with this, we dubbed it fairness tree, which is really just, the idea is not to be really too prescriptive, but really to help people navigate all the fairness that metrics that are out there in terms of how that impacts in terms of policy. So it really boils down So the most important feature in this tree is really to decide if interventions are punitive or assistive. So we really believe that it doesn't really make sense to look for fairness goals that relate to false negatives when our interventions are punitive. At the same time, doesn't make sense to look for errors across false positives when our interventions are assistive. So it's really about, are these interventions helping or hurting people? And we can think about bail determination as a compass, as a kind of intervention that hurts people. Because based on the risk assessment, people get higher bail amounts, and it's more difficult for them to get money for the bail, or they might even end up staying arrested. Same time, when we think about fraud detection in online payments, it's a punitive intervention because based on the predictions of the fraud risk, a given credit card or a payment is going to be blocked. So the risk is, are we blocking people that don't deserve to be blocked? Are we predicting as positive people that are in fact labeled negatives? This is about false positives. So it's really the cost of false positive, the cost of harm. But if we are talking about interventions that are assistive, as most of the cases in data science for social good projects, we are actually tailored interventions to help people. So we can think about mental health outreach, healthcare, personalized healthcare. We are really trying to help people that need help. So if that's the case, our really notion of fairness should be about, are we helping the same rate of people across different groups? Or are we benefiting a specific group of the population? And if we do so, are we going to widen any gap in inequalities? So it's really about false negatives. Of course, one might claim that in terms of when we talk about assistive intervention, there is a cost of opportunity of a false positive because we are helping someone that actually don't need help. That is also a valid point, but often if we care about helping people and it's an assistive intervention, we should focus on false negatives or true positive rates. So this boils down to this question. And then we also find out something that it's very interesting, which is in most data science for social good projects, we have a very limited capacity for positive predictions for interventions. So imagine that we have a data set of 200,000 individuals and we just have budget to help 1,000. So in that case, the false negative rates across all groups are going to be very high because our overall recall is very low because we can just help 1,000 people. So even if we have 100% precision on our top 1,000, these 1,000, it's going to be corresponding to a very low recall because we have a very limited capacity of predicted positives. So if we have a limited capacity of predicted positives, our false negative rates are going to be very high. So any disparities are going to be very low. So what we realize is that when we have small, lower budgets to help people, it's more about recall parity. So are we providing some assistance across different groups? So it's more about equal opportunity here. But if we are helping most people, the recall is going to be very high across groups. So it's more about focusing on false negative rates across groups to see if we are missing different people from different groups. And then we have different ways. So basically to use different denominators. So here we are just normalizing the number of false negatives by the size of the group. Here it's just by the number of labeled positives. Here it's just about the number of predicted negatives. So depending on specific cases, this is more nuanced to select between these three. The same here in the mirroring effect between these, but this is an informed discussion with our partners, and depending on different local values and different geographies, different people might care about different denominators when deciding which fairness metric should we care about. And as soon as we define a fairness metric, we should go all the way in and optimize for that. And we don't really that excuse that we are achieving this metric, but this other one is not achieving, actually is not relevant in real life and to affect real outcomes, because we boil down our metrics to the metrics that have a really most impact in our society. But as I said in the beginning, we don't want this to be too prescriptive, and this is really not the answer. It's really a starting point when discussing with these partners. Data scientists have a shared responsibility. So I often have the two extreme positions when I discuss these issues with data scientists. I often find people that say, well, I'm just a piece in a large engine, I'm just a technical person, I'm just optimizing a specific metric, I don't really care, and I don't even have the power to influence the outcomes. So the people really excuse themselves from having these discussions. But I also find the other extreme, people that are data scientists, and they assume that they are the ones that understand machine learning, they understand optimization, they understand math, and that's why they should be entitled to decide what metric makes sense in a specific case. Well, that's also wrong position, because data scientists are really crucial in these discussions, but just one stakeholder in this wider system. And it's really about making sure that data scientists are sharing information and exposing information, relevant information, to the other stakeholders, so they can make informed decisions around bias and fairness in data science for social good projects. Because if the data science explains well, discusses trade-offs, understands what happens if, for instance, is there is some sort of performance degradation over time, the data scientist has the responsibility to talk with stakeholders and say, well, we should retrain our models more frequently, there is some sort of shit in data, or we must define a process to automatic retraining. But these decisions must be taken by those stakeholders. And at the same time, when discussing fairness, data science should kind of make sure that everyone involved understand what are the trade-offs involved, so everyone can make an informed decision. So all of this reasoning about which metrics to choose, conversations with stakeholders, has a really strong assumption that we are able to audit and to measure and to detect the biases. So this is really the audit paradigm, and this is something that when I joined in 2017, Raid at University of Chicago, it really challenged me, saying like, you know, there are so many papers about, you know, bias reduction techniques, about definitions, but there is no tool out there that makes real world practitioners to easily detect and measure and really try to understand what is going on. So that's why we developed a tool, because if we measure bias continuously, we are exposing these metrics to stakeholders. And it's not because I don't believe that there is any product manager, executive person from companies that really want to be unfair. I think is that we still live in an era of blindness. So people are blind to fairness. And if we measure and we audit and we show the results, we create this awareness effect. And then fairness can actually become a KPI and a goal in organizations. So that's why we built Equitas, or Equitas. It comes from Latin, from equity. And I really invite you to go to our GitHub page. We have websites, we have different materials, and just use the tool and try it out. And we envision Aikitas to be used in these three major steps in the machine learning pipeline. Mostly after we build the models and we have predictions, we can now evaluate and select our models, and data scientists should use Equitas to unfold this dimension, which is the fairness dimension, and not just predictive accuracy metrics, and then select models with fairness and equity goals in mind. But also the policymaker, the stakeholder, you can think about governments, when they outsource to specific consulting companies or even university research groups, they outsource the development of a given machine learning model. When the government agency receives this model to be used in practice, they should audit the models for bias and fairness before accepting the model, and by the way, before paying for it, because it's really important that the stakeholders get really aware of the audits of the models. And as I said in the beginning, it's a continuous effort. Even when maintaining the system, audit should be kind of a practice. And what you need to audit your model, we just need predictions. We need attributes that define protected groups, and not often we have access to these protected attribute groups. And this is also very important thing to consider when thinking about the awareness effect, because sometimes some organizations on purpose, they don't collect demographic data, saying that machine learning models don't use demographic data. And I actually have a slide just for that. But it's really important to have access to, even if it's not for the whole population, to have a sample population that we have with these attributes. Otherwise, we cannot measure. If we don't measure, we can't improve it. And we also need labels if we care about metrics that we rely on labels. And workflow is very easy. You predict, you get the labels, you define the groups, you define your metrics, and you get the result. And Akita is available in 3 different ways. A web audit tool that can be used online, or people can download the web app, and they can run the web app in localhost. And this is more for non-technical organizations, in the sense that it's really for people to try out things in see metrics. We have a Python library that's, I think, is the go-to for the audience of this workshop. It's very easy to use. And we also have a command line tool that is more focused on kind of a batch processing. I have here a case study, a project that I worked on data science for social good in 2018. And we had access to 1 million health records of 1 million patients in Chicago from 2006 to 2018. Our label was type 2 diabetes diagnosis in the 3 years period after doctor visit. So we wanted to predict if someone, when they come to the doctor, if they will develop diabetes in the next 3 years. And for that, our label is for every doctor visits, we have a query on the next 3 years of that patient and see if there is any diagnosis of diabetes in that period, then it's a 1. If there was no diagnosis, it's a 0. And the action that we want to inform is to get personalized preventive health care, nutrition plans, because most of diabetes, when people are really low risk and they're becoming high risk, is really preventable with different lifestyle and different diet. So it's really about one of those diseases that we will for sure see a lot in terms of preventive health care. And our performance metric was recalled at a specific number of because we are based on screens and screens for diabetes. Our group metric was false omission rate, and our protected attributes was age, race, and sex. Our test set at 200,000 patients, and our prevalence was 3.4%. And we started by auditing the current practice from the doctors, and realized that the current practice from the doctors had some high false omission rate for specific age groups, and also for specific small minority groups on Native American and Native Hawaiian. They have smaller false omission rates compared to other ethnicities. In terms of sex, there was no high discrepancies between groups. So this was our baseline, so the medical practice. We trained thousands of models. We see some sort of tendency here, a trend that as we get better predictive accuracy, our false omission group across groups go lower. But in terms of disparities, we kind of see a flat trend depending on different models. We get different disparities. And here we are seeing that we are comparing the medical practices, so the orange one, with our model with highest predictive accuracy. And you can see that for every group, we get better recall. So every group will get more assistance from these interventions, but we see that in terms of ethnicity, there are some higher discrepancies across ethnicities that the previous practice. And when we think about the model, we select the model that is more equal across different groups in terms of race. This is the mustard one. So now we have a very tough decision to make. One is efficiency. If we select the blue model, we outreach and get to more people that will develop diabetes, but we will increase inequalities across different race groups. If we select the mustard one, we will have as well more efficiency than current practice for all subgroups, but we have a much more equitable kind of decision-making process. So this is really the cost of fairness. So in order to select the model with best disparity across races, we are not deploying the model that would help more people in overall. And this is the efficiency fairness tension in practice. Also, it's important to have some considerations over time. So if we think about our goal is to reduce diabetes prevalence, let's assume this is the point in time in which we deploy our models. The slope is positive for both. It means that the interventions are having effect and we are helping people across groups. But because the slope is different, we'll end up in a place in the future in which, for instance, we might have, of course, this is an hypothetical and oversimplification, but assume this rationale that we might end up in a place in which diabetes becomes only a non-white disease because we actually were able to help the white people in very different rates than the non-white people. So the question is this type of society that we want to be at the end, in which we are widening the gap between groups? Or maybe we want to think about some sort of equity intervention in which we try first to mitigate here and try to make the groups similar before, and then just make them go equal over time. And this is a continuous workflow: build models, audit, mitigation, finalize, and we iterate. And I'm not going to talk about how to reduce bias and fairness. There are many different metrics. One thing is for sure, to not remove sensitive attributes. And I still see this in the media. For instance, this is a huge executive from a huge bank saying that there is no gender bias in our process for extending credit. We don't ask whether when someone applies if they are a man or a woman. We don't ask if they are married. Well, this is really the most common fallacy, is that assuming just because you aren't using explicit attributes in your machine learning model, the model will not discriminate. We need to use this protected attributes data to compare and audit our models. And it's not just enough to remove it, not use. And we actually, if we are not collecting this data, we actually cannot measure and see if our models are getting better or worse in terms of fairness. There are different types of mitigation methods. You have pre-processing, processing, post-processing. I really believe that as we have in machine learning algorithms, we should not go for a particular method. We just try all of them all the time and test them all. In a recent tutorial we gave at KDD, we actually found out for our specific case, then regularization was actually very hard in terms of predictive accuracy. So it's the cost of achieving fairness was very high in terms of efficiency. Resampling kind of surprisingly reduced some strange positive results, and the postdoc correction in terms of thresholding, as proposed by Moritz Hart and equalizing recall and equality of opportunity, actually produced very interesting results in a public policy data science for social good setup. In an event-based driven setup, we actually didn't measure it. Things to remember: making bias and fairness and equity really integral and part of every project in data science for social good, really from the start, from scoping, is really to understand how the different phases might introduce some sort of bias, and we need to be aware of that. And even I think the way to go is really try out many different combinations of things. Not all bias metrics make sense in a specific application. Fairness tree is a good resource to try and help navigate this wide sea of metrics. Audit is really a paradigm, should be part of a continuous cycle of continuous monitoring. And just because we achieve fairness in terms of model doesn't mean that our work as data science is over, because we need to continue to audit the system and the decisions that actually affected people. There are some useful practices. This is more about making sure that everyone talks about ethical issues. We have a diverse community, diverse stakeholders. Think about all chain of data, different data sources. If that is really bad, really go out there and try to collect new data. It's really about embedding ethics in the technical processes as well in people process, because in discussions, if we don't have ethics in consideration in our background, we might have making decisions when we are data scientists that are somehow fairness blind. For instance, when we group people in a tag called others, we are introducing huge source of bias because we are imputing missing values, for instance, for a specific group. And now people that are really different from each other in practice, they have the same imputed values, and the machine learning model will treat them as if they were the same, when in practice they are not the same. This is just one example. There is some resources I want to share with you. Go out there, take. I think this presentation is being recorded, and there is a new chapter on the second edition of Big Data and Data Science, Big Data and Social Science. I'm a co-author. It's already available online as kind of a preprint. So go out there. It's very easy to read, very accessible, and I think it's that. Some links, and thank you.
Pedro, thank you very much for a very nice talk discussing very difficult problems. I like very much mainly the discussion about fairness and different perspectives of fairness. I think it's a quite difficult problem. So we have a question so far, and it's from Fernanda Silva. And what would be a good way of balancing fairness across in different groups? Faith, sex, age. Is it possible to be achieved the same level of fairness for all groups?
That's a very interesting point, because usually when we read literature assume that we care just about one attribute. So it's kind of a disjoint group. In literature, usually we see, for instance, sex, male versus female, and let's balance fairness. Race, white versus non-white. But in practice, in real life, we have different groups defined by different attributes. We might have female and male, we might have ethnicity groups, we might have age groups. So how can we achieve that? Actually, I can provide some insight. So the one way that we have achieved good results is to consider the overall the groups, what is the minimum or maximum metric value for the metric of interest, and try to optimize for these minimum or max, because that assumes that all other groups will be above or below that metric. For instance, in terms of false positive rate, you really want to maximize the you want to minimize the maximum false positive rate, because if you minimize the maximum false positive rate across all groups, you for sure will have lower false positive across other groups. That's one strategy, but usually what we do is we go group by group and we see if we get a good result across all groups.
Okay, thank you. So I have one question. I was surprised that you talk about fairness, accountability, but you never refer to explainability. So imagine if you want to grade a student, you can look for the result, or you can look for the way how he achieved the result. I prefer to look for the process that lead to the result can be wrong, but if the reasoning is okay, I will grade positive. So I believe in fairness problems, the final decision, if the explanation is okay, if that is as rationality behind the explanation, that's very important too for the fairness of a decision. So I think the explainability is quite a problem that is associated with fairness. What do you think?
I agree. It's definitely at least a confounder here, in the sense that if you have a human in the loop and the human in the loop doesn't trust the prediction, he might override the predictions in which he doesn't agree with the explanation for it.
Yeah.
And if this is systematic across specific groups, the lack of explainability or the wrong decision process from the model will influence the fairness outcome. But I want I have a different thread of work in explainability, and I think is really important. It's something that is a must. But I think in terms of fairness and measuring outcomes, especially in social good and things that affect people, is really about the following. We don't, in real life, we don't always use 0.5 as threshold.
Yeah.
So not all positive predictions, not all the predictions that the model consider that are high are going to be actually affected by the model decision, or there's not going to be, there is not a capacity for interventions in healthcare for all the patients at risk. We need somehow to sort these patients. And if we don't have a process to measure the final decision, the outcomes, how many people are being helped for that, even if we're helping people that actually the explanation makes sense, but we might end up down the road over the years produce some sort of inequality because we didn't enforce fairness. So I think it's not, what I'm trying to say is that both are necessary, but good explanations might not be a sufficient reason to decide for one versus the other if we don't have into consideration the larger picture over time, how this decision might affect the overall inequality, access to healthcare across groups, and so on and so forth.
Okay, thank you. We have another question from Rita Ribeiro. Isn't this related with the Simpson paradox? A small false positive rate in the whole population is not a guarantee with consistent small false positive rate into groups of populations.
I think that's a very good point, and the Simpson paradox is always in the mind of everyone when thinking about fairness. I think here that there is a paradox when you are making the decisions in terms of accuracy and fairness, because you might see a good false positive rate overall, but then when you go to subgroups, you actually have a really bad false positive rate in a group and not so bad in the other group. Huge disparity. So it's important to be mindful about the Simpson paradox, but at the end, I think it's most simpler way to detect, because it's really about, if we define what is our target population, is our city, is our school, is our region, is our country, is our continent, is our world. If we measure things in different levels of granularity, we might end up different results. But in real life, in real policy making, we have to make decisions. And there is a very interesting book about that. It's called Local Justice. And I really recommend it. It's a public policy book, and it really reflects that, because, you know, cities want to maximize outcomes of the population of the city. So if we are doing some sort of local intervention in data science, we need to care about the local population that are going to be intervened on that. And if that's the case, does it really make a difference if in the overall country, the false positive rates in women is equal to men, if in this particular city, it's not the case. So I think it's really about defining what is the boundary of your analysis, what is the granularity level that makes sense in specific intervention.
Okay, so thank you. Thank you, Pedro.
You have another question from Fabio. Let me.
Yeah, can you, Fabio, can you talk? Can you
Yeah, can you hear me?
Yeah,
Yeah,
yeah.
perfectly.
Yeah, okay. Well, first of all, I mean, thanks for the presentation. It was very interesting. And I found particularly interesting when you were talking about the fairness tree, maybe more as you said, as a, not as an answer, but as maybe a starting point to discuss how to evaluate fairness. But I was a little bit wondering about the fact, okay, so the first split in the tree is about whether you want to minimize hurting a set of individual or you want to maximize the benefit. But I was...
The question is not if you want to maximize one thing or benefit the other, is if what you are doing with the machine learning model, the decisions that are being done, if they are providing a benefit to people that are affected by the decisions, or if they are hurting people that are affected by the decisions. And based on these hurting or benefiting people, we want to split a little bit which metrics you look for.
Okay, but can you like phrase like the same problem in both ways? If you say, if you take the perspective of who is included in a
That's a very good point. Yeah, definitely.
Or excluded.
Yes, I actually work in a project which was in child welfare, in which we have the parents and we have the children. And the interventions were bad for the parents because the social welfare will go to knock the houses at 3 a.m. in the morning, and the social impact of that, of the neighborhoods, these are being inspected by the child welfare assistance, so it was bad for the parents. But for the children that sometimes were receiving child abuse, there were different target population. If is that the case, for sure, this is more about thinking, even before the question is, who do you care about? And then you think about if the intervention is assistive or punitive to that person. Absolutely.
Okay, yeah, okay, thanks, yes.
Okay, thank you so much once again, João.
No, Phil, I think that there are no more questions. No, I don't see. Well, let me...
I think there are no more.
Yeah, okay. Just Ricard put on chat the link for the local justice that you referred.
Thank you.
Phil, thank you very much. It was a great pleasure to have you for this lesson about fairness and social good. Thank you very much. And my...
Thank you.
Thank you, João. Bye. See you all.
Bye.
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 Thank you.
So we have Jetin here, right?
Yep.
Are you there?
Yeah, ma'am. Hello.
Hello. Can you share your screen?
Just a minute.
So Jetin is from the Indian Institute of Technology, and he is going to present us a work on data composition-based learning for electricity demand forecasting. Jetin, can I also ask you to switch on your camera, please, so that we can see you? It's more interactive to see you talk, if it's possible.
Can you see me now?
Yeah.
And can you see my shared screen also?
Slides? Yes, we can see both you and slides. It's okay. So start if you can.
So hello all, I'm Jatin Bedi. I'm doing PhD from IIT Roorkee. It is in India. It is one of the premier institutes in India. So today I'm going to present one of my work that is on data decomposition based learning for electricity demand forecasting. Here I'm specifically showing it for the case of the electricity demand forecasting, but it could be easily adopted for the other time series forecasting domain. So for the outline, I'm starting with the introduction to the data mining and the time series, and then a brief introduction to the literature survey, and then we'll be discussing the methodology and the results that I have got, and finally we'll be discussing about the conclusion, that what results that we have got from our work, this work. So starting from the data mining, as I think most of us are aware of the things, that data mining is basically defined as the process where we are extracting knowledge from the given large amount of data set. So with the advancements in the technology and the smart sensor devices, we have a large amount of time index data that becomes readily available. So the process of analyzing that data so that we can find out some important information from that time index data is termed as time series data mining. For example, here in the figure it is shown that we have a time series with the time aspect on the x-axis and the corresponding values on the y-axis. It shows that how the particular variable is changing, how its values are changing with respect to the time. So in order to analyze this data, so the basic process that we have is we have start with the raw data, then we apply a series of pre-processing steps that include data aggregation, missing values, removal, so as to get the data in a form that is to get the quality, to improve the quality of the data. So that we got is pre-processed data. Then comes the role of the feature extraction and the selection, where what we do is we generally look for the features of our interest, basically not of our interest, basically it depends upon the domain which we are working on and what would be more favorable for the target that we are currently focusing on. So after applying the feature extraction steps, what we got is that transform data. Now actually there comes the role of the data mining, that we have a series of steps or a series of algorithms and the processes that we apply so as to get the useful patterns from the data, and that patterns could be used for the future results predictions or future recommendations or for the interpretation of the current patterns. So I think this is not necessary, but for the if we are working on the time series, then in order to characterize the time series data, the four important things to look for is trend, seasonality, cyclicity, and the irregularity. So I think trend is the direction in which our time series graph is moving for a long period of time. Seasonality is the fluctuations that occurs because of the different season. For example, during the Christmas, the sales of the chocolate or the present increases, so that donates the seasonality. And the cyclicity generally looks, it's a long-term movement, and it basically it's not of a fixed period, and it spans a more larger period than that of the seasonality. And the last one is the irregularity, that could not be predicted, that may be due to the occurrence of a particular event that is not predictable. For example, any natural disaster or any pandemic situation that like we have now. So these are the typical application. I'm showing this application because I have applied this work to the applications in the field of the geophysics seismic domain, to the transportation and the agriculture. And for the today, I'm showing it for the load time series forecasting. So for the basically for the time series forecasting domain, in order to the literature we could be classified into the four different type of techniques. Earlier in the 90s, we have the engineering methods that are physics-driven methods that are used for the case of the time series forecasting, but their computational time and the generalization capabilities are a big problem because it is not easily possible to generalize them for the applications in the other domains. Then comes the role of the autoregressive model, ARIMA models, and the moving average, auto-integrative moving average, and the regression model that are better at capturing the linearities of the data. But again, the parameter optimization is also a big issue. Then comes the role of the AI-based method that includes various artificial neural networks, genetic algorithms, and also some other SVM models for the case of time series forecasting. But the important concern arises when we want to deal with the long-term historical dependencies that we have in the data. So in the recent past, a lot more models were introduced, including RNN, GRU, LSTM for the case of time series forecasting. And the lastly, one class comes that is a hybrid time series forecasting model that combines the benefits of above three techniques so as we can accurately predict in the case of time series. So here I'm presenting a hybrid approach that is combining different models so as to optimize and generate better forecasting results as compared to other three models, category of models. So this is the overall framework. This is the broad level diagram. That is, we have the historical load profile data. That is, in the present case, we are not considering any additional variables. That is, we are considering only the historical profiles that we have. We don't want any external data related to the weather conditions or the meteorological data for our prediction. Then comes the role of the data pre-processing, and lastly, we will be building a forecasting model on the top of that. This is a broad level diagram. To be more specific, this is the decomposition based framework that we have proposed. On the left hand side here, we have the load time input time series data. and the pre-processing steps. Then comes the role of decomposition. We have applied two terms, decomposition in the two terms. One is in the term of trend characterization, and second is in the term of empirical mode decomposition algorithm. That is, for the input load time series, we are decomposing it into several components so that we can use it more better for the case of forecasting. This is the, I will be explaining these steps one by one. This is just a broad framework that we have. And lastly, the predictive model that we are using. We are not using a single model for the case of forecasting. We are using a combination of LSTM and the MLP for the case of forecasting. And finally, we are summating the results, combining them so as to get the final prediction result. So pre-processing that steps that we have applied is cleaning for the missing values removal. Since we have the data for the each of the day, and they are quite in different format because it is for the last few years, so we have to combine those into a single usable format that could be used by the machine learning models. And then the data transformation. Data transformation here means that we are applying a set of transformations basically to scale the data to a range, to a common scale, to a common range. For that, we have used the min-max normalization. That works by that works by scaling the data to a range of 0 to 1. So this is the pre-processing state. So now comes the roles of the decomposition that we have applied, the level 1 decomposition. That is generally in the field of load time series forecasting, it is termed as load trend characterization. The aim of this characterization is to get an in-depth understanding of the data so that we can capture the variations more easily and more accurately. It can be done at the different levels. For example, first one is the seasonal characterization, where what we are doing is we are characterizing the time series variations on the basis of different seasons that we have in a year. And then comes the monthly characterization. We are characterizing it on the basis of a month and a daily and the timestamp, that we are considering a particular interval of the day, and we are characterizing on the basis of that, and that is termed as interval based characterization. So here in this case, what we have used is daily timestamp analysis, daily or the timestamp analysis. The reason behind this is I'm explaining this one. This is just donating that we have the complete input data set. We are decomposing it in the basis of the day's information, that we are using a different time series for the Mondays, Tuesdays, and then so on for the Sundays. The reason for this is that the data that I got is from a government, that is I'll be working on one data set that is from a government organization, and normally in the government organization they do not have that much of the resource capability. So by decomposing the data in some way, we are now working on the smaller data sets as compared to the large data set of all years. And now by using that smaller part, we are able to inference more accurately as compared to that of the complete data set. So we are just basically providing the support for a resource constrained environment, or in this case. Second reason for the decomposition is that suppose that we have the data set for the entire year. For example, in this graph on the upper part, we have the data. Now we are decomposing it on the basis of the day stamp information and aggregating that. In that case, what we are doing is now we are somehow able to take care of more long-term dependencies as compared to that of the year, because in this case we are using less data and we can span more years as compared to that in a system with a limited memory when we are using a single time series for the entire year. So this is the reason for the decomposition that we have, that is a decomposition level 1. And second decomposition that we have applied is the empirical mode decomposition. That is basically a method for analysis of the non-stationary time series dataset. It works by decomposing a time series into a set of intrinsic mod components along with a residue. That is, for example, I have given some input time series, and there's on the right hand side the figure shows that the component that I receive. The components vary in terms of frequency and the variations that have, for example, the one component have the highest variation as compared to that the component at the bottom part. So The reason behind decomposition is that by decomposing, I'm able to capture the variations more easily for the lower part as compared to that we have the complete data set for a year and we are trying to capture the variation by using a single model. So this is the case that how I'm doing the decomposition. That is, I have the data set for a day. Now I'm applying the empirical mode decomposition algorithm to divide that into the different IMF components, and then I'm creating a matrix of features that is, sorry, here it is 96, that I'm creating a matrix of 96 previous values to predict the current value, so that I can use those dependencies and look out how those dependencies are contributing to the current forecasting. And then after that, I'm doing the train and the test splitting, and then building a separate LSTM or NN model on the each of the extracted IMF, and then at the last, I'm combining those predictions so as to get the final target prediction result. So another thing is that the IMF component that we have got from the empirical mode decomposition algorithm, that varies in a number of ways. For example, in terms of the fluctuations and the variations that that are present in the IMF component. Second is the Hurst component that donates at the IMF component at the top have high Hurst as compared to the component at the low Hurst. So there is no need to train a model that is much complex for the components that are quite linear. I can't say them linear, but I can say that these are the components with some less fluctuations as compared to the component at the top. So I will be using a less complex model for that, so that I can check out that whether it will be doing the prediction more efficiently or not. So based upon the different components, I'm using the different models, that is either to choose the LSTM or the neural network model. And after training those models, we are finally combining to then the results of each of the model to get the target prediction result. One of the basic and the most important feature of the empirical mode decomposition algorithm is that it is lossless. We can again combine the IMF obtained by the decomposition to get the original signal. That's why here we have used the empirical mode decomposition algorithm for the case of the final prediction. So in order to compare, there are a lot more models are available in the basically research in the literature review that uses the same empirical mode decomposition algorithm for the prediction. So I have compared the results for those with those models. First one is the model that uses the empirical mode decomposition algorithm for the data decomposition, and then train an LSTM model for each of the IMF, and then finally evaluate the prediction model. Second one is the case that we are decomposing the data set on the basis of different IMF components. Then we are calculating the average of those IMF components, and then we are then the research work is subtracting that IMF average IMF component from the original time series signal, so as to check whether the noise part is removed from the initial time series signal, and then it is training that prediction model on the basis of those newly extracted time series models. So that is the second case, is that we are calculating the average and then subtracting it from the original time series and then checking how it is predicting. And the third one is our model that we have used is to decomposition level 1 and the 2 and different LSTM and the NNS based model for the case of time series forecasting. So for the cases of evaluation, what we have used is we have the historical timestamp data from the Australian national electricity market, and that is for the sampling date for the data is around 30 minutes. And we have the data set is available for 5 different states, but we have used the data set for the one state, that is Queensland. And in order to evaluate the model, what we have used is different measures. That is the root mean squared error and the mean absolute percentage error. And for training our model, the software and the hardware configuration is that we have trained the model on a 1-2 system with a tensor with a 64 GB RAM and the Xeon processor with 48 cores and 2 TB hard disk. And that's the result that we have got on the data set for each day, that we have the model 1 and the model 2 and our proposed model. In each of the case, we are getting a performance improvement The performance improvement is not that much high, but it is quite high in the sense that when we are decomposing the data and we are training our model on the less data and we can support the resource constrained environment. So in that opinion, by keeping in mind that things, we can say that the model is working perfectly fine as compared to that of the other two models. So this is just the forecasting results. On the bottom part, we have the number of data samples, and that is and the orange part shows that what we have the true values, and that is the train predictions, and the test prediction is shown in the orange and the green part, and the blue part is for the true values that we have. And that is the another prediction results for the on the same data set. And I've just included them to give you a demonstration that how actually how well actually good results we are getting from the prediction. So this is the work that we have got about. That is, we have performed the decomposition on the data set in terms of itself. On the one end, it is doing on the basis of the day stamp information, and second is on the in the terms of a decomposition algorithm. And then we have also got the reduced complexity in the sense that we are using the less complex model for the case of prediction, when we have IMF component which are less complex as compared to that of the other components. And the proposed model also outperforms the other two state-of-the-art hybrid demand prediction models by providing an average 1.63% of average prediction error. So this is the case, and some of the important references that are there that I have included, and this is the paper which I have used for the comparisons are there. Thank you.
So, thank you, Jatin. We already have one question here from Irina.
Okay.
She congratulates you on using Australian data. But the two questions are, the first one is, what is the advantage of IMF decomposition compared to wavelet decomposition? Have you compared the two?
Actually, for the case of the IMF and the wavelet, what I have done is that my previous work that is in a journal that is on decomposition and comparing the results of the different decomposition-based algorithm. So in that case, I have also worked on the EMD and the VMD and the wavelet algorithm. And the VMD empirical mode decomposition algorithm works well and better than other wavelet-based decomposition algorithm. That's why I have included this for the case of my current decomposition.
Okay. The second question is, you train many models, one for each day of the week, and it is an ensemble, one base learner for each IMF component.
Yes.
This is complex. Is it beneficial compared to using one global model, such as one for all days of the week, or one without any decomposition, such as LSTM, NN, or RIMA?
Actually, it matters in the terms of accuracy that we are focused on. In the case of decomposition, without decomposition, if we train a model, and by decomposition, if I'm building a model, separate model, I know that it is increasing the complexity in the sense that because we are training more model as compared to that of having a single model. But it is working very fine in the case when we have the different variations depending upon the day stamp information. For example, I have worked on one data set that is from India, and the variations in the weekdays, that is Monday and the Tuesday, is quite high as compared to that of the Sunday. So in that case, what it is doing is that the variations at the Sunday are affecting my overall prediction when I'm using a complete model. So in that case, I thought since I have worked on, I thought that this will work fine for the case of decomposition for the complete day. And I think this will also work fine if we consider the interval-based decomposition also. But yes, I admit that it is increasing, it is giving you more complexity in the terms of number of models that we are training. But in the terms of accuracy and also in the terms of resource constrained environment, if we think, then in that case, I can recommend this one if you have a resource constrained environment.
Okay, I have one last question. Did you consider to see or make special models for holidays, national holidays? For instance, I imagine that the demand should be different. Did you consider the hypothesis of considering national holidays?
No,
Or
I haven't considered that for the national holidays because actually it is in the terms of Australian data and I don't have that information in the terms of holidays and I'm frankly saying I haven't considered and I don't even think of that because I think this is a good idea to consider those things also because the variations in that case will be quite different from others.
yeah, imagine a New Year's Eve or something like that. So, okay.
I can consider those things also because it will somehow help me.
Okay, any more questions? Should we move forward to the next speaker? So the next speaker is Sumayoti. I don't know if I spell it right.
Yeah, that's correct.
Yeah, from Arizona State University. He's going to present us a work entitled Mitigating Bias in Online Microfinance Platforms, a case study on kiva.org. So you can share your screen.
Yeah, sure.
And let the camera on.
Yeah, just give me 1 second. I think I need to quit the app to give access. I'll log back in.
Yeah.
Are you able to see my screen?
Yeah, yeah.
Yes. Yeah, thank you for attending this talk. My talk will be based on mitigating bias in online microfinance platforms. And this study is performed on this platform called kiva.org. And this is jointly done by myself and Amit Reza Alvari when we were both students at Arizona State University. And so Kiva, for those of you who don't know, is one of the most popular microlending platforms. And it is a kind of platform where borrowers from different parts of the world, they come and they propose their own projects to receive funding from different lenders. And it's a pro-social platform in the sense that lenders contribute small amounts of funds to the projects they are interested in for specific borrowers, depending on the projects they submit, but they do not expect any return on the investment. They just get their money back when the projects are completed. And so there is no profits involved in this lending process. And there can be like different kinds of these loans are categorized into different sectors like agriculture, housing, retail, or even it can be for very personal reasons like buying a vehicle for aiding the business. So these can be from small amounts like $200 to quite large amounts. And it depends on the kind of like projects that the borrowers are proposing. And so what happens with these platforms is that there exists a lot of disparities in which that occur when different kinds of projects are posted, and lenders can be unknowingly biased towards specific projects or specific borrowers coming from different parts of the world. And so it's inherently not very easy to understand what kind of project attributes or project traits contribute to successful funding. So a successful funding meaning that the project, the loan amount requested by the borrower gets fully funded by multiple lenders. And so there have been several studies, like it's quite a popular platform which tries to understand what attributes to a successful matching of these lenders to borrowers. And typical traits include like the credit worthiness of borrowers, as in most finance platforms, or the history of the borrower loan repayments. And these loans can also be undertaken as part of groups. And it has been shown that when borrowers request these loans as part of groups, they are more successful to be funded. And they're not just more successful to be funded, but they also have a higher likelihood of completing the project. So not all projects get completed. So in some sense, in few cases, the lenders might not get the money back because the project was not completed. But beyond this platform and these features that have been studied through various prediction models to predict the success of funding a loan repayment even before the project starts, people have studied what causes some of these projects to be favored more. And there have been it has been shown that through several research works and through empirical evidences that cultural differences and geography, these have been like one of the major determinants of pro-social lending. And even so, loan features like the amount of the loan requested or the gender of the person who has been requesting the loan, they contribute to the likelihood of successful funding. But the main, the recent studies have showed that the reason behind which these platforms were initially started was to make the world more flat, the flat world hypothesis that, that says that these kinds of platforms enable more equality among borrowers, irrespective of where they come from. But empirical studies have shown the opposite of that, in that people tend to, there have been close relationships between the borrower and lender countries and borrower and lender geographies. And so pairs of countries tend to favor more, which defeats the purpose of having these platforms as mitigating the effects of what would happen often in offline activities. So the basic questions we started while starting this investigation was, are there any hidden bias among lender preferences? And it's very difficult to study these based on just the data from Kiva, because Kiva just gives you the attributes of the loans and the lenders, and that might not always be sufficient to reason about whether there exist biases among lenders. And if so, are they specific to, like I mentioned, that sometimes lenders prefer specific sectors? Is it true, or what's the reason behind such specific sectors? Or is that there are particular sectors that are actually clustered amongst several countries and these countries get funded more? So understanding these hidden biases can help actually improve recommendation systems. And because most of these platforms allow recommendation systems that recommend these projects to different borrowers. So making these diverse and fair can be one of the steps towards mitigating the existing bias, which can often be a result of unknown attributes. And so what we did was we basically collected the data from Kiva, which gives us the data for the loan features like the currency, like I said, the gender, and there are several other attributes like the project sector and some more integrated details about the specifics of the project. But we go beyond that now to collect some external data based on World Bank metrics that accounts for the borrower-lender connections, like whether the borrower country was colonized by the lender country, and also borrower country specific attributes like what's the loan access availability in the borrower country itself. And these attributes were selected so as to understand what's the so as to be a sort of capturing the lender perceptions about the borrower projects, because often lenders would do their own research beforehand to understand whether they would be interested in specific borrowers. So these kinds of attributes, I will go on to explain what the attributes are, but sort of capture these aspects of preferences of the lender towards these borrowers or the borrower countries. And the goal here has been basically trying to measure the impact of these features on the success of likelihood of the project getting funded. And we use this funding time attribute as a proxy for measuring the success. And the funding time is basically the difference between the time when the project was first listed on the platform and the time when the project gets fully funded after several iterations. And so that's basically the funding speed at the time, you could say in one sense. And that's a proxy for understanding what happens even prior to the start time of the project. So what we did was we collected around 1.3K loans, and these were from 216 lender countries. So multiple lenders can actually lend to one particular project. There were around 57 borrower countries, 7 languages. The average loan amount you can see is around 836, and the funding time is around 12 days. And this data is basically available from all the public data available. So we did not have any specific private data for this project. And what we did was we started with a preliminary regression analysis. Just start with see the impact of these attributes on the funding speed. And you can see at the outset that there are some attributes which are more important than the other. Like, for example, distance and GDP difference seem to have lesser impact than the effect of colonization, like I mentioned. And colonization is an external factor, not present from the Kiva data itself. And similarly, migrants of borrower country, the number of migrants of the borrower country present in the lender country also determine the success of these of the likelihood of getting funded faster. And similarly, women ratio have the ratio of women in the country applying for these loans that tends to have a significant negative correlation, which means that this factor has a positive effect on the funding speed. So the funding speed gets lower when the women ratio factor is higher. But this does not include, from all studies that we see on understanding the attributes towards mitigating bias and fairness, often one of the attributes can be a determinant behind all of these. And for this, we studied the sector attribute. So evidently we can, for these two models, the first model M1 does not include sector. So we remove the attribute sector, but for model M2, we include this dummies of the sector, because there are around 14 sectors we considered, and we consider those sectors as dummies in this model. But at the outset, we see there's not much difference in the two models. So it's not very clear whether including the sector attribute does make any difference in the kinds of impacts these different features have. But then the next question is, let's see about how do we, if we consider data for each of these sectors separately, then having specific project attributes specific to each of the sectors, does these have different impact on the funding speed? So what we did was we created 14 different models for each of the sectors, but for brevity or for explanation, I showed just 3 models. For example, let's consider the data in which we consider all the loan attributes for the services sector as one group, and the loans belonging to all the other sectors as another group. And we do this for all the sectors. And then we can see that some of these attributes might not have even the same relation to the funding speed. For example, we can see for services sector, the colonization seems to have a negative effect, while for the other 2 sectors, it does seem to have a positive effect. And that's true for also the effect of loan access or the availability of loan funding in that country, or the affordability of loans in that country. So such factors tend to play different roles in different sectors. And the question is, these tend to have an impact on different borrowers who who post projects for different sectors. And these can be quite unknown to the borrowers, because these are perceptions of lenders, and they can contribute an effect towards projects for belonging to specific sectors. Additionally, we also find that sometimes understanding these effects through these 14 different regression models can also be cumbersome and not very robust, because these results are affected by the varying sparsity of the data available for each sector. So not all sectors will have equal number of loans. So it's not very easy to compare the results outright. And so now the question is, can we design more robust metrics to understand the impact of these factors on the funding times? And this is where we try to take some hints from recent advances in causal inference. And so what we do basically is that for each sector S, we partition the data into two halves, like we did before. One, the loans belonging to sector S, and one, the loans not belonging to sector S. And the average treatment effect, the tau that we see here, measures the difference between the potential outcome of the loan belonging to sector S and potential outcome of the loan not belonging to sector S for a particular loan. And observe that this Y1 and Y0, you can only observe one from the data, because on a loan can only belong to one sector at a time. So the other factor is not observed. And so for these reasons, it's not very easy to directly measure this average treatment effect, because you can only measure one from the data. And so we need to come up with some approximation mechanisms that can deal with such unavailability of data and still be able to measure this metric. So what we basically do is that we pick up one of the estimators. So there are different estimators that can actually be able to capture this average treatment effect, and we pick up one of these, which is known as the doubly robust estimator. And this basically uses some machine learning techniques to estimate this tau. So what it basically does is that it computes, so without going to very intricate details, I'll just briefly overview that it computes three kinds of factors here. One is the mu. The mu is basically the expected value of the loan belonging to what the value of that potential outcome of the funding time should the loan belong to sector S given its attributes, and mu 0x is the opposite. Given the same attributes, what would have been the expected potential outcome if it were to belong to if it were not to belong to sector S. And so these, like I said, these two models have to be approximated because we don't observe both of these for all the loans. And we also have this propensity model, which is the probability of this loan belonging to this particular sector. And so with these three factors, the doubly robust estimator can actually estimate the average treatment effect. And all we need to do is now approximate these functions, mu and e, by machine learning models, given the data. So what we basically do is that for measuring the mu, that's the expected outcome of given the feature attributes, we use Bayesian linear regression because this somehow helps avoid the sparsity effect, like I said, for different sectors, because different sectors will have, some sectors have sparse data, and this allows to nullify some of the factors which are not helpful for some of the sectors. So for each loan sector, we use separate models to estimate this mu1 and mu 0x with these linear regression models. And for estimating the propensity score, W, we just use a logistic regression because that's a binary outcome. And once we have these three functions, we can now input any loan attribute, the feature values, and we can get this average, average treatment effect using this estimator. And this estimator, we picked up this estimator because it's some very nice properties of being doubly robust, even when one of the functions is not very, even one of the machine learning models failed to produce a good outcome, the other, it can still have the same variance and same bias. So that is why we picked this up. And what we do is now we measure these this estimator with some of the baseline estimators. So the naive one is, let's not consider any estimator, just consider difference in means of these potential outcomes for the two groups. The baseline is when we consider, instead of considering this Bayesian regression, just consider a linear model and measure this average treatment effect as the difference between these two outcomes and average them over all the instances. And the last one is the one we mentioned right now. So what we did was, what you see is that these are the sectors that we consider, the loans belonging to these different sectors. The AT is basically the tau that we're measuring, standard deviation, and these are the three estimators. And what we find is that when we compare these three, the retail, the housing, arts, personal loans, we find that there are definitely differences in the funding outcomes. Where we find that the funding time for arts loans are almost 6 days faster when compared to all other sectors with our model. And this is considering that different lenders have different perceptions. There is bias existing because of pairs of countries. And given all these perceptions, we come to find that, yes, there are sectors where these loans can be different, can be favored more. And when we come, so this is more robust when we compare the simple regression models that I mentioned at the beginning. So red ones basically denote the differences we observed from the regression models that I mentioned, because these are more accurate in the sense that these are estimators are better than considering simple individual regression models. And so this is at least an outline, a way to show that there exists some disparities, the discrepancies, when people from different sectors with having different backgrounds come to post different projects. So the question is, how can we produce a step to even start mitigating these biases without even hurting the chances of successful matching? One of the ways easiest ways is to just use some regularization constraints. So what we did was we have this spike and slab regression model for predicting the funding times that we earlier used for the metric, consider that same model for now predicting the speed of this or the funding time. But now we consider a balance means constraint where we say that let's now forcefully fix. So DS, these two partitions are basically the loans belonging to the sector and loans not belonging to the sector, and we forcefully constrain that these loans belong to different sectors should have the same outcome. Basically, this is a simple linear regression model, and we expect that the outcome should be the same. And we add this regularization to this model. And next, when we try to now use this model for predicting the funding speed, the first one is a simple linear regression model. The second one is the linear regression considering only the Kiva provided loan attributes without the external factors. The third one is just a simple spike and slab. And the last one is where we consider the regularization that I mentioned. We find that yes, when we use this constraint, there is definitely a drop in the performance. So lower values means that they indicate better results. But the drop in performance is not really far off from when we just consider the spike and slab. As you can see, the last column, there's a drop in performance. And this goes on to show that yes, even with these constraints, we can achieve prediction problems. We can try to predict some features, try successful matching with these predictions, which are not far off, but still be able to now do a fair amount of introduce some kind of fairness in these prediction outcomes. And so building this was one of the steps of showing that how bias can exist in these platforms, even when they can be decentralized, where they can be somehow partially unfair to all participants, but still people tend to have some biases without knowing the impact, their aggregate impact on the borrowers. And so some of the future directions could be, instead of now, we should building separate models for each sector. But the goal probably would be to build one model and try probably use that in a platform. And that can be achieved by extending this Bayesian regression model with somehow parameterized priors or driving these two empirical Bayes using data. And one of the goals of these studies is to now devise probabilistic recommendation models where these fairness constraints can be incorporated into priors. Right now, we did not incorporate these constraints into priors, but inside the regression models itself, but these can be incorporated into recommendation models where we use priors with these fairness constraints. And the reason we chose this platform is because this platform is, like I mentioned at the beginning, is pro-social. And so we expect that the lenders are not motivated by returns, but the question is now, can we extend these understanding and also similar mitigation towards platforms where the lenders expect some ROI and the biases can be even augmented because there is an inherent tendency to get more ROI. In that case, how do we define what is fair and how do we measure bias? And that is a probably extending question that's very difficult to measure. And I think such studies can help actually take a step towards these questions. And with this, I would end my talk. Yeah, please feel free to ask questions.
So thank you. Thank you for your talk and your interesting paper. Do we have any question from the audience? Well, while there is no question, I was wondering regarding your...
Can I ask a question?
Who? I don't see, sorry.
Sorry.
Sorry. Yes, there is one question.
Yeah, I was. Yeah, I mean, thanks for the presentation. First of all, I was quite interested in the causal model that you designed. So the treatment variable is just a binary decision whether to fund or not to fund the project, right?
Yes.
So it doesn't take into
the treatment variable is not the decision. The treatment variable is the sector. So the treatment variable decides whether the sector belongs to, whether the loan belongs to that sector or not. So the treatment variable is basically assigning the sector to the loan. So that's the treatment variable. The outcome is the Y0 and Y1 are the funding. So the binary, it's not the binary outcome. The treatment is the sector of interest.
Oh, okay. Now, yeah, I see. Right. Okay. Yeah. Thanks.
So my question was regarding more the data set that you gathered from Kiva. Were there a large spectrum of loans amounts? Were they are kind of uniform? Don't you think that that should make some influence on the speed of getting the loan?
Yeah, so that is one of the like confounding variables that we tried to also analyze. So in the paper we did plot the distribution of the funding amounts, and we did some filtering based on some of the project attributes and the countries. We tried to keep a few countries, but from the distributions that we observed, there was no observable skewness towards any particular amount. So more or less, most of the projects that we selected, without knowing the funding amounts, tended to have a flat distribution. So in our case, the funding amounts, we removed that as a factor, for a confounding factor for the bias. But definitely, yeah, that is one factor when we consider 1.3K loans, but when you consider large amounts of loans, that can be a factor that needs to be controlled for, in addition to problems in the sector. I agree with that. Yeah.
Yeah, thank you. So, are there more questions? If there aren't, should we move forward to the final talk of this session? Yeah. So it's Fabio, right? Fabio Zanaro. Yeah.
Yes.
Yes, from University of Rome. He will present us a paper on a discussion about left realistic critique of the practical value of adopting machine learning systems in criminal justice. So please go ahead, Fabio.
Yeah, right. Okay, thanks. Thanks for the introduction. Yeah, so what I would like to present and discuss today is the topic of fairness. But I would like to discuss the topic of fairness from a different perspective than usual. So instead of discussing about the fairness of a certain given adopted machine learning systems, I would like to discuss about the fairness of adopting a machine learning system. So normally we are given a machine learning system. So when we talk about fairness, we normally discuss about the metrics of fairness, so how to evaluate or how to estimate the fairness of our system. So the kind of problem that we try to solve is what sort of metrics should we use, or sort of metric makes sense. But now I would like to sort of take a step backward in this discussion and consider the problem of adopting a machine learning system. So this leads to more high-level questions, such as what is the role of a machine learning systems, and a little bit more specifically, what could be the political value of adopting a machine learning system. And this last is the question I would like to address. So in order to discuss about this question, okay, there are two terms that I want to define. So the first one is a machine learning system. So in this discussion, I'm gonna restrict the attention to a specific subclass of machine learning system. So whenever I'm talking about machine learning system, I'm referring to supervised system, which are supposed to model a functional relationship between a set of inputs and a set of outputs, and models that are learned by minimizing a loss function given some data. So this is a quite restrictive definition of machine learning system. So we all know that we could easily extend it. But the main reason why I'm restricting to this category of system is that this sort of system, supervised system, especially like modern deep learning systems, are among the most popular and the most widely adopted in the real world. The second term that I want to specify is political value. So what do we mean by political value? We mean any sort of value that a specific artifact or technology expresses, or any sort of value that a technology makes it easy for its user to express. And so we would like to try to understand what sort of value adopting a machine learning system may carry with it. So underlying this question is, of course, an important assumption, the assumption that artifacts and technology in general cannot be politically neutral, but that they carry with them some specific value or some specific set of value. So we are not going to discuss the political value of adopting machine learning system in general, but we will consider within a specific context, so in the context of criminal justice. So why criminal justice? Criminal justice is a very wide field, but it contains a set of problems that are very relevant for machine learning in that they may easily conform to the machine learning paradigm. So these are problems such as parole assessment or risk assessment, recidivism assessment, where somehow we are required to try to evaluate or to judge an individual based on a set of features with respect to the risk that it poses to society. But there are also other problems in criminal justice more related to optimization, like optimal police deployment or optimal use of law enforcement resources. And indeed, criminal justice has had a long relationship with first statistics and nowadays with machine learning, to the point that its role is being brought to the foreground in several firm machine learning applications. Okay, how are we going to try to uncover these political values that may be embedded in the adoption of the machine learning system in criminal justice? So we are going to try to do it by performing a critical assessment of machine learning systems using the categories and ideas from left realism. So left realism is a criminological theory proposed in the 1980s for the first time by two scholars, Lee and Yang. And it was proposed as a sort of middle ground between two other criminological theories of the time. One was left idealism, which has been partly surpassed and left behind. And the other one is law and order, which is instead still quite relevant. So what we will do is to try to analyze certain issues that are particularly important in the field of criminal justice, see how these two opposite positions of left realism and law and order answer to these issues. And then we will try to understand how machine learning fits in this spectrum defined by left realism and law and order. Okay, so the first thing I'm going to do here is to try to give you a brief overview and a quick understanding of these issues that are relevant in criminal justice. So this is, of course, going to be a very fast explanation of these topics and these issues. Of course, a longer explanation is available in the paper. Okay, so the first issue that we consider is the problem of how to approach crime. And even on this point, we can already observe a clear difference between a law and order position, which tends to prioritize the problem of directly fighting crimes, often addressing just the effects of crime more than its causes. And on the other hand, left realism that instead prioritized understanding crime and tried to uncover links of cause-effect in order to act on the causes more than on the effects. Another important difference is how these two stances see individual committing crimes. Law and order tends to rely on more like simplified sociological categories, for instance, defining criminals as a sociopathological individual or under-socialized individuals, while left realism tends to avoid strict characterization and prefers more complex explanation of behaviors of individuals. Connected to this issue is also the issue of which types of crime a theory of criminal justice should be concerned with. Law and order tends to have quite narrow focus on what sort of crimes should be of interest, and specifically it tends to center its attention on violent crimes. And along with this comes the tendency to use authoritative definition of crime, so having precise explanation of what constitutes a crime and what it does not. On the other hand, left realism instead has a more flexible approach. It tries to widen the view of crimes that should be taken in consideration, putting, for instance, certain emphasis on what are called white-collar crimes, not just violent crimes. And it's also more aware of the problem of how to define crimes, aware of the need of more like dynamical definition that may evolve in time and may take into account the gap that often develops between authoritative definition and perception of crime. An issue that is very relevant and close to machine learning is the issue of data use and data interpretation. Law and order tends to have a more pragmatic relationship with data, so trying to collect and use data directly for the aim of enforcing policies. Left realism instead prefers a more careful and cautious approach. It tends to be more aware of the subtlety and the bias that there may be in data collection, and so it proposes a more careful use of this data in decision making. One point which probably is very relevant nowadays, and where the distinction between these two criminal justice theories is more clear, is on the matter of policing. So law and order tends to favor what has been called military policing, so a use of law enforcement resources in a unilateral way in order to contrast crime under the direction of law enforcement agencies. On the opposite position, instead, left realism favors what has been called a consensus policing. So the idea that the use of law enforcement resources shouldn't be unilateral, but should be, at least in part, community-driven and definitely strongly community-integrated. And connected to policing is also the issue of accountability. So how to keep law enforcement agency accountable for their actions. On the side of law and order, there is a clear priority on police efficiency, and this often leads to accept certain degrees of covertness or secrecy regarding decisions taken by law enforcement agencies. And the opposite stance, instead, left realism puts much more emphasis on the problem of the democratic overview of the decision of law enforcement agency, and so it tends to emphasize the need for transparency. So these are 5 issues that are very important in any sort of criminal justice theory, and here we have sort of outlined the differences between these two contrasting theories. The thing that we're gonna do next is to try to show how machine learning systems, understood as supervised learning system, tends to align with one of these two positions more than the other. And specifically, we will try to illustrate how certain features of supervised systems put machine learning and the decision of adopting machine learning system closer to a law and order approach to criminal justice more than a left realist approach. And again, this presentation again is very short and synthetic, but on the paper there is more argument in favor of each one of these points. So coming to the problem of how to approach and confront crime, supervised system, as we know, tends to focus much more on finding correlation within the data and optimize prediction. So by their very nature, they disregard the discovery of cause and effect links. And this is already one first point where supervised system tends to be more in line with a law and order approach that disregard cause and effects. But there is also another characteristics of supervised systems that is quite important under this point of view, and is the fact that we need data having clearly defined, well-defined labels. And again, the use of labels may easily align with the use of simplified or oversimplified criminological categories to explain the data, which again is typical position of a law and order stance more than a left realist stance. If we consider the types of crimes that criminal justice should take into consideration, we know that supervised system, and specifically deep learning system, modern deep learning system nowadays, rely on a large amount of data for their training, as well on a clean labeling of the data. And this again may align supervised system more with the law and order stance. And this is due to the fact that often we may have data only for a limited set of crime of interest. And this may lead to a sort of self-reinforcing positive loop where our focus is only on certain crimes. We can train machine learning system only on these crimes. And indeed, we will have more data and more historical data about the same crimes. Coming to the issue of interpretation, we also know that machine learning systems, as any sort of statistical system, is grounded on clear statistical assumptions, but we also know that often there is a use of machine learning system that is irrespective of this assumption. Often we see deployment of system just as pure decision-making tool. And again, this follows the pragmatic stance of law and order, which may use machine learning system just as pure instrumental and legalistic tools to process the data. Coming to policing, it's easy to see that supervised system, but in general, probably any sort of machine learning system is more suited for supporting military policing than consensus policing. And this is just due to the fact that a machine learning system is a system designed to analyze and crunch data, and it was not designed to support any sort of community integration. And finally, on the issue of accountability, also on this point, we are aware that different types of supervised learning system, and again, here I'm thinking specifically of deep learning system, have poor interpretability. Many of them are considered just as simple black boxes. And again, this allows for a use of machine learning system in support for opaque policies or policies that are determined just on the ground of efficiency. So there is quite strong alignment between supervised learning system, as we have seen, and the values that are expressed by a law and order position. There is a last issue that I have not presented in this listing, and this is the problem of adoption of new technology. Actually, as discussed in the seminal work on left realism, there is an interesting analogy between adoption of new technologies in the 1980s, and in that time we refer specifically to the adoption of closed camera televisions, and adoption of machine learning system in the 2010s. There is an analogy in the sense that both of them are new technology, both of them are promoted on the ground of efficiency, rooted in this idea of exploiting data intelligence and allowing remote control of communities or society at large. And in both cases, these technologies may lead to promote what has been called the fire brigade mentality in law enforcement, which again is characteristically of a law and order position. So this fire brigade mentality is the idea that it is possible to fight crime or control communities and societies, surveilling society remotely and acting only surgically when need arises. And again, this is in contrast to a left realist position instead, which would promote this stricter and deeper integration between law enforcement agencies and communities. Okay, so overall, what I hope I was able to present to you is a quite simplified analogical analysis of machine learning systems. This is simplified, of course, for two reasons. The first reason is that when we have discussed machine learning system, we have always considered them as simple functional models. But we know that there are other branches, other extensions of these models that are very active nowadays. So we could consider models from causal machine learning or interpretive machine learning. And if we do so, some of the statements that we have made about the alignment of machine learning and law and order may not stand so strongly. And there is also simplification, of course, in how we consider criminal justice, in the sense that, of course, criminal justice theories are much richer than the simple dichotomy that we have presented here. But in any case, the main point of this discussion, this presentation, was trying to highlight how a simple decision of adopting machine learning system actually comes with clear implicit political bias. And these biases may be overlooked in the best case, or in the most dangerous case, they may be exploited. There are in particular two dangers that we discussed in the paper. So the first one is this danger of naive adoption of machine learning systems. So a decision of adopting machine learning systems just on the ground of technological enthusiasm. And on the other hand, there is a more subtle risk of instrumental adoption. So this is the idea that it's possible to adopt machine learning systems in order to justify specific policies. So this would be the case of justifying, for instance, focus on certain crimes just because we have data that may be processed by machine learning models, or the attempt to justify opaqueness on the ground that machine learning models are black boxes. So both these dangers are present, and even a simple decision as a decision of adopting and employing machine learning system. So the hope of this presentation is raising some awareness of the fact that there are political biases inscribed or embedded in machine learning system, and hopefully fostering a little bit of discussion also about this issue. Thank you for listening.
So thank you, Fabio. We have already one question from Ellen Tucker that says that it seems from your talk that many machine learning approaches do not offer anything for the left realistic approach. Can you think of any ways, sorry, because now we have another question, any ways that machine learning can be used to improve, for example, community-based policing? For example, by empowering communities with data?
Yeah, well, the main point is not really that machine learning doesn't provide any sort of improvement, but the fact that we have to be aware of the political value that is connected to the adoption of machine learning systems. So even a supporter of left realism would, I think, agree with the use and the deployment of machine learning systems, as long as certain values such as transparency, such as a community-wide discussion on how to use, what to measure, is guaranteed. So yeah, the point is, okay, it's not like left realism is some sort of neo-ludist position that is against new technologies. It's more about how to use them.
Okay, we have another question from Ricard. Thanks you for such a thought-provoking talk. Interesting that the mere fact of deciding to use supervised machine learning as we know it aligns you with one school of thought. Any ideas of how another data-driven paradigm more aligned to left realism could look like? Perhaps making causality take the center and not just correlation?
Yeah. Oh, sorry.
Not entering on whether it would be more or less desirable, just wondering how many unexplored paradigms can be out there.
Yeah, like in how I was suggesting, I was trying to suggest this, yeah, in the end, in the discussion. So there may be models that are closer to a left realist position than this simple functional model approach. And yeah, definitely like causal machine learning models may definitely be closer to a left realist approach in that they try to discover or understand the underlying causes of crime and act on them instead of acting on effects. And yeah, actually, I mean, there is a thread of research and literature on causal fairness, and I think that some of the proposal in that context may align very closely to a left realist position. Again, another, I think, simple way to align more to left realism is, for instance, trying to deploy interpretable models. So this would guarantee more transparency, more interpretability. Another possibility that I was suggesting is like transfer learning. So this would prevent us from narrowing our attention only on crimes for which we have data, but it may allow us to transfer knowledge also to other crimes. I guess also probably more awareness about like the statistical foundations of any sort of machine learning model would something that would be promoted by a left realist position in order to really have a more careful and clear understanding of what these models are doing.
Yeah, we have one more question from Ellen. It says, thanks, a very interesting talk. Maybe a knowledge discovery approach would be more progressive, where the focus is on discovery rather than on automation.
Instead of, sorry?
Automation.
Oh, yeah. Oh, yes. Yes. I mean yeah. Yeah, I agree in the sense that, yeah, most of these, functional models are mainly focused on prediction. And yeah, definitely, understanding, so knowledge discovery, causal models would probably all be useful approaches from this perspective. Yeah.
Any more questions? I personally have to say that I really enjoy reading your paper also. I think it's it makes us think about how we are applying things and how we should not be totally blind for these issues. So if there are no more questions, we are at the end of this workshop. And I hope you have all enjoyed the workshop. I don't know if the other organizers want to say something regarding the workshop. Ricard, Irina, João. Nope. Irina also no, and João, I don't see him.
So I would like to thank first all participants, all presenters, everybody that submit to the workshop, all the program committee that help us in reviewing papers and select papers. So thank you very much. See you next year.
Yeah, I hope you enjoy it as much as we did with these sessions. Okay, see you next year. And I do one question that I believe that we put the slides online last year. You have put the slides online. I don't know if you are going to do this year or not. So, but in case we are, we ask you afterwards, okay? Okay, bye.